All right, good morning. Good. We're going to look at 14.3 today. Now, this is a very important topic. This is going to be the foundation of a lot of things to come. We'll be talking about these things called the partial derivatives. So if you think back to a one-variable function, if y is equal to f of x is a one-variable function, then when we talk about how y is changing, the only way we can attribute that change to is to attribute it to x, right? In this case, how y changes is affected by x only. So talking about the rate of change or the derivative is a very, very straightforward thing. Derivative is, as you all remember, f prime of x is df dx, limit h goes to 0, f of x plus h minus f of x over h. Okay? Now when we talk about functions of more variables, then things get more complicated. Let's look at a two-variable function first. Z is equal to f of x comma y. All right, so think back to the heat index as a function of the temperature and the humidity. The heat index is affected by the temperature of the air and the relative humidity. So when Z is changing, there are two factors involved in that change. How the temperature feels like outside is constantly changing. And as the temperature of the air is changing when the sun is rising right now, for example, and the humidity, we got two things going on. So at this moment here, the sun is rising. So the air temperature is rising. But the sun is also boiling off the humidity. So the humidity is dropping. So we got one thing going up, one thing coming down. And those two things are fighting against each other to give us the true feel of the temperature. And pretty soon we'll probably have to start talking about wind chill instead of heat index. But when we get there, we'll change the example. Now very often we want to know, how is Z affected just by X, and how is Z affected by just Y? How Z is affected by just X or just Y. And when you take the derivative, if you look at this definition here, now we got two things changing. It's a very complicated thing to deal with. So the idea is to hold one of these variables constant, allowing the other one to change. And this is exactly the same as, very similar to the idea of traces and contour maps and all of that. You hold something constant, allowing the other things to change. And so this is the idea of a partial derivative. If z is f of x and y, the partial derivative of z with respect to x So this is where we hold y constant, allowing x to change. And the definition of the derivative is used again, just like a one-variable function. When you hold y constant, allowing x to change, you're back to a one-variable function. So the partial derivative of z with respect to x is written as f with a subscript x. The subscript tells you what variable is changing. Fx tells me that I'm holding y constant, allowing x to change. And this is also written this way. In the old derivative notation, we use df dx. Now we have two variables going on. We use a different kind of d. So you write this a really strange looking d this way. Very scripty or very deformed d if you want. So a funny looking d. Be sure that you differentiate the two different d's here. And this, you treat it just like a good old regular derivative. Limit h goes to 0. F is a variable, a function of two variables. We're allowing x to change. So we do this on the top. All right, so we let x change, holding y constant. And this is exactly the same form as the one that you're familiar with. And in this operation here, y is a constant. Y is treated as a constant. The partial derivative of z with respect to y, same idea. Now we write f with a subscript y. Y tells you what variable is allowed to change. In that notation here, there's your funny-looking d, the function f, funny-looking d, the variable that's allowed to change, y. And in the limit definition, same thing. You hold x constant, allowing y to change. Here we treat x as a constant, allowing y to change. And this idea extends to 3-variable, 4-variable functions, and so on. Right? Every time you see a subscript here, that's the variable that's allowed to move. Everything else is not allowed to change. Okay, example. f of xy is equal to x to the 8th, y to the 5th, plus x to the 3rd, y to the 1st. That's an 8. And let's find the two partial derivatives. To find fx, remember y is treated as a constant. So in this first group here, x to the 8th times y to the 5th, you should treat it like 2 times x to the 8th, because this guy is a constant now. It's a number, right? So if you have 2 times x to the 8th, you know that constant doesn't matter. You simply take the derivative of the part involving the live variable, 8x to the 7. Does that make sense, how I got that? Yes? Okay, y is a constant, right? What about here? What do we get? 3x squared times y. Very good. Because y is a constant. So this is treated like 2 times x to the 3rd. Let's just make this a little nicer looking. 3x squared y. Let's find a partial derivative with respect to y. This time x is a constant. Now in this function here, we have a constant times y to the 5th. 4 times y to the 5th, right? So the constant multiple doesn't do anything. Derivative of y to the 5th is 5y to the 4th. Here we have constant times y. Derivative with respect to y is simply that constant in front of y. So we get x to the 3rd. Does that make sense? Yes? Okay, so see, there's no trick to it. You just got to keep track what is a constant, what is not a constant, while you do the usual differentiation. And as usual, suppose that f of x is positive. This means that as x is increasing, while y is a constant, f will be increasing. F is increasing as x increases. An important part here, while y is held constant. Okay, positive rate of change is increasing, as you all know. And the x down here tells you what is changing. Positive increasing as x is increasing, while y is held constant. And you know the same thing for negative, 0, and all that. And fy, same idea. This time you hold x constant, allowing y to change. fx and fy are slopes of traces of the function z is f of xy. right? So for example, when you have f of x, f sub x means y is constant. Say something k, for example. So that's a trace when we hold one thing constant and we look at how z and x are changing. And for example, let's suppose on the z and x plane, the graph looks something like that. Right, so that's our trace. When you hold y constant, whatever comes out, that's our trace. So at any particular point, if you look at the slope, that slope right there is fx. How z is changing with respect to x. So this is the standard idea that you already know from one variable calculus, just the slope at some point. And same thing for fy, right? You look at the trace in the z and y plane, and then you look at the slope. So all of the stuff you know about derivatives still as the same as before. It's a slope of something, some kind of graph. Questions? Okay, let's do another example here. We can also do implicit partial differentiation. For example, here I have an implicit function yz plus x natural log of y is equal to z squared. And we would like to find the partial derivative of z with respect to x and the partial derivative of z with respect to y. You remember how to do implicit differentiation? Yes? No? Maybe? Okay, let's do a quick review of that. Thing here to keep in mind here is that z is an implicit function of x and y. Notice that in this equation, we could never isolate z by itself. There's no way I could rearrange this equation to get z equal to something with just x and y. Because I have z showing up in two places, there's no way to totally separate z out by itself. So this is the key idea, just like you might remember. Let's find the partial with respect to x. Let's do this on the next slide. To find the partial derivative with respect to x, remember we just go ahead and take the derivative of both sides of that equation with respect to x, partial derivative. So in our equation here, partial with respect to x, the left-hand side of the equation and then partial with respect to x of the right-hand side of the equation. Okay, now we take the derivative as usual. Remember, this means y is a constant now. So here we have a constant times a function of x. Differentiating this first group here, we get whatever that constant multiple is, and whatever z is with respect to x. Does that make sense how I got that? Yes? Good? Nod your head if yes, so I can see. Good. Now same thing here. Second group here, when I take the partial derivative with respect to x, y is a constant. So this is a constant. This is no different than 2x. Derivative of 2x is 2. Derivative of constant times x is constant. Right? So simply the constant natural log of y. How about the right-hand side? What do we get? 2z, is that it? Partial of z with respect to x. Right, the chain rule, because z is a function of x and y, so you got to use the chain rule here. All right, now we find this guy right here. Solve for partial z, partial x. Very simple. Natural log of y is equal to, let me subtract this over here. All right, so I subtracted y times the partial of z with respect to x to the right-hand side, and then I factor that out. So, partial derivative of z with respect to x is equal to natural log of y over 2z minus y. Questions? Any question with how I got this? Okay, let's find the other one. Partial with respect to y. Same thing, right? You take the partial with respect to y on both sides. This time x is a constant. So what's the derivative with respect to y of y times z? What rule do I have to use? Product rule, right. Remember, z is a function of y. Right? Z is implicitly a function of y. So you have two things multiplied together, both depending on y. We have to use the product rule. All right? So, first, derivative of the second plus the second. And what's the partial of y with respect to y? It's what you would expect. 1, yeah. Right? So this part, remember to use the product rule. And this guy is 1. We'll simplify it after We finish the whole thing. Okay, so these two account for the derivative of y and z with respect to y. What's the derivative with respect to y, partial derivative with respect to y of x times ln of y? X over y, right? Good. How about right-hand side? 2z, partial y. Any question with all these things here? Good? All right. Now let's solve for that. Solve for partial z with partial y. So let's see. This is a 1 now. We have 2 of these here. Let's bring this guy over. And let's kick these 2 things to the right-hand side. Minus z minus x over y. Factor this out and divide it by the excess baggage. And we get negative z minus x over y over y minus 2z. And you, of course, you could simplify a little bit more, but that's good enough. Okay, questions? Are we okay with the idea of a partial derivative here? Okay, now we're going to do second order derivative. So let's go back to that polynomial function we looked at earlier. X to the 8th, y to the 5th, plus x to the 3rd times y. And we already know from earlier example that f of x is 8x to the 7th, y to the 5th, plus 3x squared y, and fy 5x to the 8th, y to the 4th, plus x to the 3rd. So we know that already. We did this earlier with the first example, and we found these 2 things pretty easily. Now we're going to deal with the second derivative. And it's just like what you've been doing here. You take the derivative of the derivative again. Let's start with the second derivative with respect to x. So when you see 2 subscripts here, this is exactly what you think it means. It means that you take the partial with respect to x, then you take the partial with respect to x one more time. So you do it twice. Both times you use x as the variable. The other notation is kind of weird. Sorry, partial with respect to x of partial f partial x. So this is funny looking d squared f funny looking d x squared. Okay? So this is a derivative of fx with respect to x. All right, so what do we get? What do we get out of the first term here? 56x to the 6th, y to the 5th. Very good. And the second group here, 6xy, good. All right, now let's do fyy. Partial, partial y, partial f, partial y, funny looking d, square f, funny looking d, no squared, y squared. So you take the derivative of fy with respect to y again, treating x as a constant. So this is pretty easy. 20 x to the 8th, y to the 3rd. What about x cubed? What do we get out of it? Right, there's no y here, right? This thing is a constant as far as that step is concerned. So this here grants us a 0. Okay? There are two more partial derivatives. fxy means you take fx, now you differentiate with respect to y. So in the second step here, you treat y as the variable and x is a constant. Now here's where the other notation gets kind of annoying. fxy means you do partial with respect to x first, then you do partial with respect to y. X and then y. Here, same thing. You did this first and then you do that. Now when you write in this notation here, you get your funny looking d squared f. Downstairs, you see partial y, partial x. So notice that in this notation here, the order is clear. Right? The order of partial derivative is very clear in the fxy notation. You do x first, and you do y. But in the other notation here, it's reversed. You have to read from the right to the left. In this quotient notation here, x happens first, y happens next. And that's because y is showing up in the outer, it's the outer part of the operation. Remember, you always perform this first and then you do that. All right, so this is taking the derivative with respect to y of f of x. fx, 8x to the 7, y to the 5th, plus 3x squared y. Y is the variable, x is a constant. So what do we get out of 8x7 y to the 5th? Good. 40x to the 7th, y to the 4th. Everybody agree with that? Yes? Nod your head so I can see. Good, thank you. Second group, what do we get? Yeah, 3x squared. Let's find fyx. Remember, in this notation, in the subscript notation, the order is left to right. So this is take the derivative with respect to y first, and then x. In the other notation, this is the second operation. This is the first operation. So that's funny-looking d squared f. Downstairs is funny-looking dx, funny-looking dy. Right? You read it backwards. Y first and then x. That's the partial with respect to x of fy. Fy is 5x to the 8th, y to the 4th, plus x cubed. And what do we get? We get the same thing, right? So you get 40x to the 7th, y to the 4th, plus 3x squared. It's exactly the same thing as we just got, taking the opposite order. And that's not a coincidence. It's not a coincidence that fxy is equal to fyx. This is called the symmetry of mixed partial derivatives. And this symmetry holds whenever the function is continuous. In other words, if f is continuous at the point AB, then fxy at AB will be equal to fyx at AB. Okay, and that's always true whenever the function is continuous at that point. This, by the way, is what's called Clairaut's theorem. Clairaut was a French mathematician, and he proved that this is the case. We don't have to worry about the proof for that theorem. It's in the book if you're interested. But the important thing to take away is that whenever that function is continuous at that point, the mixed partial will always be equal. This is a polynomial. It's always continuous. So the mixed partial will always be equal to each other. All right? Okay, let's extend this to a 3-variable function. And you already know how to do it. F of xyz is equal to e to the xyz. Let's find. Let's find f of xyz. fxyz. Same idea. Each time you take partial, there are 3 variables now, so you treat the other 2 as a constant. And you do that 3 times. And this tells us the order. X first, then y, then z. That's variable, right? The first step, we treat x as a variable, y and z will be constants. Second step, we do y and treat the other 2 constants, and so on. All right, first step, fx. Remember, y, z are constants. So what do we get? Say that again. Right. Remember, exponential here, derivative of exponential is whatever that exponential is, times the derivative of the power, right? We use the chain rule. So we get that because it's exponential. Then the derivative of the power with respect to x. If y and z are constant, this is 2x. Derivative of 2x is 2. So derivative of constant x is constant. Constant. So yz e to the x y z. Now we do the second part, fxy, right? fxy. In the second step here, y is the variable. X and z are constants. Even though both the x and y show up here, we only read the last one. The last one tells you the variable at that step. X and z for that operation right here is equal to they're both equal to constants. How do we do this? Product rule, right. One more time, product rule. Okay, so you can look at it as a product of this guy times that guy. Product rule first, yz times derivative of exyz with respect to y. So that's e to the xyz. Chain rule, derivative of the power with respect to y, xz. So that's first derivative of the second plus the second exyz. Derivative of yz with respect to y, we get just a z, right? So far, so good? Yeah? Let's simplify this before we do the next step. Let's see, I could take out as e to the xyz. That seems pretty obvious. First group, I get x, y, z squared. Second here, I get a z. Do it one more time. F, x, y, z. This means last one is the live variable. Z is a variable. X and y are constants. What would this look like in the other notation, the quotient notation for derivative? Upstairs is easy, right? The funny-looking d cubed, f. What about downstairs? In what order do the variables show up? Reading from left to right. Right. But when you say d, you mean the funny-looking d, right? Yeah, the funny d, funny d. Funny d z, funny d y, funny d x. Remember, in the other notation, we read it right to the left for the true order. Now, for this problem right here, does that order really matter? Is the exponential function always continuous? Yeah. So knowing Clairaut's theorem, the order really doesn't matter, right? But anyway, let's just carry this out in the order we have been doing. All right? Z. So this is a partial with respect to z of this thing right here, exyz, xyz squared plus z. And this is the product rule again. Function of z, function of z. All right, so first, derivative of this with respect to z, 2xyz plus 1. Do you agree with that? Yes? Good. Second one here. So this is the first derivative of the second plus the second, xyz squared plus z. Derivative of e to the xyz with respect to z, we get xy e to the xyz, right? Agree? So this gets a little bit messy, but what you can do is to factor out the e to the xyz, and then just simplify whatever's left. You should get 3xyz plus 1 plus x squared plus y squared plus z squared. Wait a minute. No, that's not right. xyz. What? How about let's just not simplify? Okay, that's good enough. Good enough. Good enough. You get the idea, right? You can simplify next. Now, when you do this on WebAssign, toss that in first. If it doesn't work, then you do simplify. And make sure you do it right. Don't do what I just did. Okay, does the partial derivative make sense? Yeah? Be careful with your bookkeeping. If this is the first time you're doing stuff like that, write down what's a constant, one step at a time. Okay, that's it. Have a good weekend. See you Monday.